Let's consider the same problem statement. You have a list of questions, and each question has a point value and a brain power required to solve it. You start with 0 points and brain power, and you want to earn as many points as possible by solving the questions. However, you can only attempt a question if your current brain power is greater than or equal to the required brain power. If you solve a question, you earn its point value, but you lose brain power equal to the required brain power. You cannot attempt a question if you don't have enough brain power, and you cannot regain brain power once lost. What is the maximum number of points you can earn? Let's start by considering a brute force approach. We could try every possible combination of questions to see which one gives us the most points. However, this approach would have a time complexity of big O2 to the power n, which would be impractical for large values of n. Next, we can try to simplify the problem. We know that we want to maximize our points, so we can focus on the questions that give us the most points. If we sort the questions by point value in descending order, we can start with the highest point value question and work our way down the list. This way, we can be sure that we're always attempting the most valuable question possible. But what about brain power? We need to make sure that we have enough brain power to attempt each question. One approach is to keep track of our current brain power and only attempt questions that we have enough brain power for. However, this approach doesn't take into account the fact that some questions might give us more brain power than we need. For example, if we have 6 brain power and a question requires 3 brain power, we could attempt the question and end up with 3 brain power remaining. But if the next question requires 2 brain power, we could attempt it even though we only have 1 brain power remaining. This is because the first question gave us more brain power than we needed. To take advantage of this, we can use dynamic programming. We define a state as the maximum number of points we can earn starting from a certain index I in the list of questions. We use this state to compute the next state. The brain power we have at each index depends only on the brain power we had at the previous index and the brain power we gained or lost from attempting the previous question. So, we can use the state of the previous index to compute the state of the current index. The C++ code to implement this approach initializes a vector to store the maximum points at each question and loops through the questions in reverse order, starting from the last question. For each question at index I, it computes the maximum number of points that can be earned by either solving the current question or skipping it, and stores the result in the dp of I vector. The dp of I vector stores the maximum points that can be earned from question I onwards. To avoid going out of bounds, the code uses minimum jump plus I plus 1, n to ensure that the index of the next question is within the range of questions. Finally, the code returns dp of 0, which represents the maximum number of points that can be earned from the first question onwards. The time complexity of this dynamic programming approach is big O(n), where n is the number of questions. The space complexity is also big O(n), since we use a single array of length n plus 1 to store our intermediate results.